See, so you talk about that. No, so you have C decrement the value or decrement, and then you just pass that number into your code that changes the real amounts. So C is doing all the math, and you're just having the assembly code. Changes where it started with that was some information. And then once it gets to less than when it goes below zero, yeah, it's numbers in the bound. I mean, it probably still works, but below zero would be more general. And also make sure because there's like a little sticky. You try to decrement below zero. You should be decrement below zero. So now I have to start adding, right? Go and add it. So it only adds up to go above zero, and your code starts to subtract. So it never goes up to the maximum value. So you mentioned it can go up to max. Yeah, you need to make some need to add something that makes it go all the way up to like 16 million. Because like when he was like, that's what you're talking about. Oh, variable for what?
No, for I think for zero and now.
For zero?
I don't know.
I don't know.
The problem is
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. I'm a little sleepy. My dad called me at 7 o'clock this morning, woke me up before I wanted to. He's on a cruise right now. He's going from Miami to Portugal, and he called to say hi and tell me about all the fun that he's having on the cruise. So he's like, how's your week going? How's everything going? I'm like, well, I'm doing midterm soon. My students are really stressed. He's like, oh, okay. I'm gonna go take another tequila shot. I'm like, okay, have fun, Dad. So yeah, I couldn't go back to sleep after that. So I'm a little sleepy today, but okay. So today we're starting a new topic. So let me just get this out of the way first. So everything we talk about today will not be on the midterm. Okay. So midterm exam is going to be on Tuesday, April 22nd, which is a week from today. So the cutoff point for that midterm was what we finished last Thursday. Okay. So today we're starting something new. So what we're starting today is going to be on the final exam, but not on the midterm exam. Okay. So you can kind of, don't fall asleep. Don't tune out. This stuff's still important. But you can, just know that it's not going to be on the midterm for next Tuesday. Okay. Speaking of the midterm, hopefully everyone got my email yesterday about the midterm exam. So same deal as the first exam. So you can bring your a cheat sheet, 8.5 by 11 inch, both sides, same as first exam, bring your calculator, writing utensil. I posted a study guide for the exam as well as a practice exam. So the practice exam that I posted is basically the exam that I gave 2 years ago in this class. I somehow lost that file for the first exam, but I have it for the second one. So I posted there. I don't have solutions for it, but if you do want to give the exam a try and kind of talk about the exam in office hours, kind of talk about your approach, your solution, that's probably the best way to kind of go about that. Okay. So all that's available for you guys. I do expect this compared to the 2023 exam, I do expect this one going to be a little bit shorter. I am going to cut out one question from the exam just because we kind of rushed through Fourier transforms a little bit. So you can expect. So I think the practice exam, you'll see there's one question on Fourier transforms. You won't have to worry about that on your guys' exam. Okay, so it's going to be focused on the integral calculus theorem, so Green's theorem, divergence theorem, and Fourier series expansions. And so those are what I would focus on. But for conceptual questions, you can still expect maybe something from Fourier transform. Okay. So take a look at the materials if you haven't yet. I know you guys have a busy week. I think there's quite a few other exams going on this week. But maybe end of this week on the weekend, check out the study guide, check out the practice exam, just to help you guys study for this. Okay. All right. And so besides that, I did post one more homework assignment, homework 6. So that is due this Sunday. So solutions for homework 6 will go up on Sunday night, kind of before the exam, just so you have that for your studying as well. Okay. All right. Any questions on the exam coming up, or just anything before we get started today? Yes.
So everything we learn on Thursday should cover everything we need to know for homework 6.
Yes, exactly. Yeah, so you guys should be fully equipped for homework 6. So what we're going over today has nothing to do with homework 6. Right, any other questions on anything? Okay, all right, so let's go ahead and get started. All right, so this last unit that we're going over in this class is kind of a interesting one. So the way 308 kind of works is that, we have to get through differential equations, we have to get through Laplace, we have to get through Fourier, and then kind of this last topic is usually something that's kind of like dealer's choice. So when I teach 308, I like to do a little bit of probability and statistics because I feel like it's a subject in math that's very undercovered in your other math courses, but does play actually a very important role. So I think traditionally, you guys learn this in your lab courses, but the way they kind of teach in the lab courses, they kind of expect you to kind of know a lot of it before. Either maybe you learned it in high school or maybe you kind of picked it up from other places. But so for the last part of 308, we are going to be going over introductory probability and statistics with kind of a focus on kind of tools and knowledge that you guys should know as kind of practicing engineers. Okay. Okay. And this kind of leads into kind of some of the the research work that I've done in the past too, based on kind of uncertainty quantification. So, this subject is, something that I wish I kind of had more of when I was a student. Just because, when I was a grad student, I was kind of just thrown in the fire and to like figure all this stuff out. Like, oh, I haven't really learned all this stuff. Okay. So probability and statistics is really interesting. And honestly, I think it's something that should be kind of taught as a separate class because of how relevant and honestly how different it is from a lot of the math that we've done so far. Okay. So let me start with this statement. So up until this point in the class, okay, and really honestly, probably up until this point in a lot of your other classes, with the exception of maybe your lab courses, we have been assuming that all of the numbers that we've been given, all of the formulas that we've been given are what's called deterministic. Okay. So deterministic may be a word that you've heard before. Maybe this is kind of the first time that you've heard of it, but basically deterministic, all that really means is that, whenever you're given a number, that's the only value that that number can have. So a number is a number. Okay. Okay. So anything that you're given is basically assumed to be kind of the truth. And there's no room for any variance or any kind of uncertainty in the numbers that you're given, right? So the lengths for certain dimensions are given as x. Height is given by y. The viscosity is given by x, right? And so everything is deterministic, and that makes things convenient for math, because when we solve equations, that means that when we solve an equation, or we solve a differential equation, algebraic equation, if all of the values that go into the equation have only one possible value, that means our solution also can only have one possible value. Okay. So this is kind of the way that most math is taught, right? Because when you're kind of learning how to solve differential equations for the first time, when you're learning how to take a Fourier series expansion for the first time, it's hard enough, or there's kind of enough going on in that process where, you know, it's usually not practical to consider uncertainty in that situation. But, you know, in reality, you know, this often is not true. Oftentimes, you know, what you often take to be is just kind of having only one value or one truth, you know, can really be kind of a range of different values at the same time. Okay. So let's give an example of one thing that, you know, most people would probably express as a deterministic value, but in reality, there's actually a lot of variance and there's a lot of uncertainty associated with it. Okay, so let's talk about commute time. Okay. Or basically the amount of time it takes for you to go from your home to campus each day. Okay. So when someone asks you, you know, how long does it take for you to get from your home to campus, then, you know, most of the time people will say, oh, it takes me about so and so time, right? So maybe it takes me about 30 minutes or it takes me about 40 minutes, right? Right. And so in this case, you know, the 30, that's kind of what we interpret as kind of well, at least kind of what we perceive as kind of the deterministic value. But we know, right? So every day your commute time is always just a little bit different. It's hard to really pin it down, you know, even to the minute, but, you know, never mind the second or the millisecond, right? And what's the reason for this? So the reason for this is because oftentimes your commute is complicated by certain things that you cannot predict. And so the traffic, maybe that's coming in at the time, maybe the traffic lights, maybe there's pedestrians or construction, right? And so there are certain factors that you are uncertain about that change the day-to-day value of this number here, of this parameter. Right. So maybe one day, you know, you get to campus a little bit quickly, right? So maybe you get in 25 minutes. But maybe the next day it takes you a bit longer because, you know, there was construction in your commute. So maybe it takes you 35 minutes, right? On average, you know, maybe they all average out to be 30 minutes. But you know, if someone were to ask you, you know, tomorrow, what is going to be your commute time, you wouldn't know because you don't know what unexpected or uncertain things are going to occur, you know, on your commute for tomorrow. Okay. And so in this situation, you know, if we were to represent your commute time as a variable or some kind of data, right? You know, it wouldn't be appropriate to represent it as a deterministic variable because it's something that changes day to day. And so mathematically, the way that we represent your commute time is we say that your commute time is what's called a random variable. All right, so you know the word random, you know, I honestly its definition has kind of changed over time, and so you know when I say random, you know that's not to say that commute time can be, you know, completely random, and so it doesn't vary from 3 seconds to 30 hours, right? There's still some rules that kind of, you know, guide the permissible or, you know, likely values of the commute time. So even though it's random, it's not completely random, right? And so let me kind of just make that distinction. So there's still some trends and rules that it follows. And so there's going to be a mean value. There's going to be a standard deviation to the random variable. Eventually, probably after the midterm, we'll talk about things like probability distribution functions, right? So it's going to follow a set distribution, okay? But it's random in the sense that every time that we observe this variable, so every time we take a commute to school, its value is likely going to change from day to day, from moment to moment, okay? That's what it means to be random. All right, so that's the opposite of a deterministic variable. So for a deterministic variable, every time we observe it or every time we measure it, it always comes up to the same value because it is deterministic in nature. But for a random variable, every time you measure it, every time you observe it, every time you calculate it, it's always going to be a little bit different from each other. Okay. But still follow some rules. Okay, so that's kind of what this whole unit is about. And because in engineering, when you are working with these very kind of complex physical systems, you're designing them, you're analyzing them, a lot of times, the variables that you are working with are going to be random. And so they're going to change, right? Measurements naturally are just random in nature, right? You can measure the exact same thing twice with the same ruler, right? And you might get very slightly different answers, right? And that's just based purely on the precision of your measuring device, right? And so knowing how to account for these things, knowing how to kind of deal with them in engineering context, I think is a very important skill for engineering. Because oftentimes it can kind of change how you do things or how you kind of compute things. And those changes can often be pretty important in terms of what you budget for, how much factor of safety that you do. So having a good grasp of probability and statistics is a good, really, really good skill. Okay. Okay, any questions on this so far? Okay, good. Okay, so first thing we're gonna do, we're gonna kind of start with the very basics. So we're gonna start with this idea of data representation. Okay. So when you have a random variable, every time you observe that variable or measure that variable, its value is going to change. And so oftentimes, you want to record that information or represent it in a way that is, that kind of makes sense, that represents that data. Okay. So the most basic way to kind of record the value of a random variable to kind of present it is through a data table where you just record all the values of the variables. Okay. So for instance, let's take our example of our commute time. Let's represent that in a data table. Okay. So let's say that we record our commute time, week by week. Okay? So we record it maybe over a 4-week period. So week 1, week 2, week 3, week 4. And then for each week, we're going to record our commute time kind of day by day. So we have our commute on Monday, our commute time on a Tuesday, on a Wednesday, Thursday, and Friday of that week. Okay, so this is kind of the most basic way, and probably the first thing that you're going to do when you first start recording data. So you're going to open up like a Google Sheets or something like that and just input the numbers into the table, just like this, right? So let's say Monday of that first week, let's say our commute time was, 31.54 minutes. Tuesday, maybe it's a little bit faster, maybe we have 28.15 minutes. Wednesday, maybe it's 30.44 minutes. Thursday, maybe there's an accident on the freeway, so maybe it takes you 38.91 minutes. And Friday, let's say you go a little bit faster, 26.11 minutes. Okay. Okay, so this is kind of the most basic way to do that. And then let's say that you repeat those measurements the next week. Okay. All right, so for those of you who have taken lab classes before, this is probably the way that you first recorded the data. So you run your experiment. Oftentimes you're running the experiment multiple times and you're recording the data in the experiment in a table like this. Okay. Okay, so data tables are great. So they're kind of the most convenient way to record data. And if there's ever a situation where you just want to look at all the data, all the raw data, you're probably going to be looking at it in some kind of data table form. Okay. The unfortunate thing is that with a data table, it's really difficult to see any kind of trends in the data, right? So it's really hard to compute the average of the data or maybe the standard deviation. Okay. So it's usually not a great way to kind of present information, present data. Okay. And if you kind of go back to your lab courses too, right? So most of the times, you're not writing your lab reports. You're not putting just the raw data in the lab report. Maybe you're putting it in the appendix. But for the actual write-up itself, you're probably graphing the data in some different way, or you're analyzing the data in some different way. So there's usually a better way to kind of present data that kind of shows certain trends or certain statistics. Okay. But you got to start somewhere. You got to start by recording data, and data tables are the best way to do that. Okay. Okay. All right. So let's start talking about some graphical ways to present data, where we can start to see some trends and some statistics. Okay. Let's talk about the histogram first. Okay. So histogram is a great way to present data that can show you, the relative frequency of certain values that the data takes. Okay. Because most times, you know, when you have a random variable or you have some kind of random measurements, right? Certain values or certain bands of values are going to show up more commonly than others. And you can express that in a histogram. Okay. So the way to kind of, build a histogram is to, first of all, you need to sort your information, you need to sort your data, or you need to sort your measurements into various, we call them bins. Okay. Where each bin kind of represents a band or a range of values that the data can take. Okay. Okay, so kind of continuing on with our, with our example of our commute times, let's say that we make separate bins, each bin with a range of kind of 2 minutes. Okay. So let's say that we make a bin for, maybe 25 to 26 minutes for our commute. And then 27 to 28 minutes. 29 to 30 minutes. And then 31 to 32 minutes. And then we'll do one more, 33 to 34. Okay. So each of these is a separate bin that we can kind of, that we can use to build our histogram. All right, and so the histogram, what it's going to show you is that it's going to show you how many times your data falls into each of these bins, each time that you observe, okay? Right? And the histogram will show you this by kind of different bars of different heights, okay? Okay, so let me kind of show you what that looks like. And so, of course, this is kind of just using made up data. In reality, you would actually record your data and do this, but, I just kind of want to show you what a histogram would look like, okay? Okay. All right, so let's do it like this. So let's make our histogram, maybe look something like this, okay? And so along the horizontal axis here, I'm going to list out each of the different bins that we defined above. Okay? So let's say we have a bin for 25 to 26, 27 to 28, 29 to 30 minutes, 31 to 32 minutes, and then 33 to 34 minutes. Okay. And so in histogram, what you're going to see is that, you're going to have a bar that comes out from each of these bins, and those bars represent, how many times the data fell into that bin. Okay. Oftentimes, what you're going to see is that you're going to have one kind of dominant peak. And so that's going to be the highest frequency. So let's say most of the time, our commute time is going to fall between 29 and 30 minutes. Okay. And then from there, things usually start to kind of taper off. So let's say, we have our bin that looks like that, 27 to 28, maybe something like that. Okay. Rarely, maybe we have some really good days where our commute's really short, 25 to 26, okay? And then sometimes, let's say our commute is a bit longer, so then that would be 33 to 34 minutes, something like that, okay? And of course, you can create more bins, right? And so you can always create more bins to kind of fit the entire range of your data. Okay? So let's say that we also have a bin from 35 to 36 minutes. And let's say that we have, maybe one commute within that area. So we have kind of a very short bin. Okay. So even with just this kind of, fairly simple kind of representation here, we can start to see some information about the trends in our data, right? So this information here, you could pick it out from the data table if you kind of have an eagle eye, right? So you can kind of see which ones are appearing most often. But oftentimes, it's a lot more, visually pleasant and visually pleasing to look at a histogram rather than just a huge table of different numbers, okay? And that's kind of the whole point. So the whole point of kind of, different ways to represent your data, right? The whole point is to, make it easier for you and make it easier for your readers or whoever's going to be reading your reports to view these trends and view these statistics. Because it's, oftentimes it's not going to be immediately clear, when you just look at just a huge pile of data. Because right away, you can look at this histogram and say, probably the mean value, the average value is maybe somewhere in the ballpark of 29 to 30 minutes, maybe a little bit higher because, the peaks are kind of shifted to the right a little bit, right? And we see a little bit of, the trends in terms of, the variation. And so, your commute time is going to be as little as 25 minutes or as big as 36 minutes, depending on the traffic at the time. Okay? That's the whole point. So the whole point of this is to kind of highlight these trends, highlight these statistics and make it easy for readers to interpret. All right, any questions on histograms? Okay, good. All right, so another popular way to represent data is to use what's called a box and whisker plot. I always thought it was kind of a funny name for a plot. Okay. Okay, so the whole idea of a box and whisker plot is to, again, to kind of show and represent trends in the data, but to kind of focus on kind of different things. Okay. So box and whisker plot is kind of centered around this idea of a quartile of the data. Okay. So what are quartiles? And so, whenever you collect a bunch of data, you can order that data from in either ascending order or descending. Okay. So let's say we took our data points from our commute times, and let's say that we recorded this over the course of 4 weeks, and so we have 20 data points, right? And so if we took all those commute times that we listed it from the shortest commute times to the longest, we have an ordered list that looks like the following. Okay. So 1, 2, 3, 4 dot 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 5 I meant to skip 4, but I just continued on with 5. Let's say 17, 18, 19, 20. Okay. Okay, and so at the top of this list, let's say we have the shortest commute times. And then on the bottom, we have the longest commute times. Okay. This order is important. And so you want to make sure that there's a certain order to your data, right? And so the idea with quartiles is that, you know, once you've ordered the data from either ascending order or descending order, you then are going to split your list into 4 different sections, right? And so we're going to have, you know, maybe the first 5, right? And then maybe another 5 in the middle, right? Maybe another 5 that kind of covers, you know, like this, right? And then maybe a final 5, in this case 3. Okay, so we basically split our data into kind of 4 equal-sized chunks. Where each of these chunks, you know, because they are equal size, right? We can describe them as kind of the first quartile, the second quartile, the third quartile, and the fourth quartile of data. Okay. So that's all quartile is. So quartile, I think is a fancy word, but it's you know, it just represents kind of different chunks of the data, you know, quartile, which is, you know, represents maybe the best times, second quartile, which is the next 25%, third and fourth. Okay. Maybe it's a term that you guys might have heard before is percentile. And so I think percentile is the same idea, except instead of 4 different chunks, you know, for percentile, you're splitting the data into 100 different chunks. And so you can say you're you know, maybe the 50th percentile or maybe the 71st. You know, in some ways it represents, you know, you're better than a certain amount of the data. Okay. Okay. So box and whisker plots, you know, is designed to kind of show these different quartiles in a very kind of convenient way. Okay. Okay, so let me kind of show you what that looks like. Okay, so the nice thing about box and whisker plots is that they are very compact, and so, you know, they don't take up kind of a full 2 dimensions like the histogram. Okay. Okay, so for a box and whisker plot, just like the name implies, you're going to have a box. Okay. Okay. Where the vertical axis here represents, you know, values of the data. Okay, so your box is meant to represent kind of the middle 50% of your data. Okay. Right. And so that's everything in your second and third quarter. Okay, so that's the box, right? So the box represents kind of the middle 50% of all of your data. Okay. Now the whiskers kind of come off the box, right? So you'll often see box and whisker plots kind of have a long whisker just like that. Okay. And so each of those whiskers show what's kind of deemed as kind of outliers of the data. Right. So maybe on here, right? Let's say that this whisker down here, maybe this is the fourth quartile. Right? And the top whisker here represents the first quartile. Okay, so basically, with the box and whisker plots, we use these, we use this kind of representation to represent, where the middle 50% of the data is, where the top 25% of the data, and the bottom 25%. Okay. Okay. So that's what the box and whisker shows. But oftentimes, these plots are modified so that you can see the median of the data as well. Okay. So oftentimes in the box and whisker plots, you'll have a line that kind of goes right, in the box. Sometimes it's right in the middle, something shifted up and down. Okay, and we'll talk about kind of why that is a bit later. So this red line here represents the median of the data set. Okay, so if you're reading kind of scientific papers, that kind of utilize a lot of data, box and whisker, just because they are pretty compact and they can show you, a lot of information. Okay, and oftentimes, with these box and whisker plots on the vertical axis, right, those will have numerical values like this, so exactly kind of where the whiskers represent, right? So where the most extreme values of the data are, what the median of the data represents, so on and so forth. Okay, any on box and whisker plots? Okay, so we're not going to do too much with box and whisker plots in this class, but I thought I would mention it just because it is so common. So you see it in so many in so many papers, so many scientific reports. So it's always good to represent that because it's box and whisker plots is one thing that I've seen a lot growing up and going to school, but I wasn't familiar that it was actually connected to this idea of the quartile. So, something good to know. Okay. Okay. So we've gone over boxes. It's not the only ways that you could use to record data. So I've gone over this too, just because I think for those who are familiar with the traditional box plot, traditional scatter plot, so I didn't want to go over again, but these two are sort of statistics in the data that I think are useful. Okay. Uh-oh. No, I think the mic might be yeah, kind of phasing in and out of it. So, yeah, let me know if it kind of phases out. So now that we're kind of done with kind of the qualitative representation of data, let's talk about quantitative tools for AMP data. All really nice. Yeah, with some with these are start with hello. Okay. Okay. Yeah, this webcam is kind of janky, but yeah, hopefully we can stay connected for a while. Okay, so the mean of the data set is nothing more than just the numerical average of all the entries within the data set. Okay. All right, so the mean, you guys have computed averages probably your entire life, but let me give you the formula again. Okay. So oftentimes, we represent the mean with a a symbol with a line over the top. Okay, so that line over top usually means average. Okay. All right, and so the way we compute that is, let's say that we have n number of entries. Okay. We're going to do 1 over n multiplied by just the summation of all the entries in the data set. So you have summation from 1 to n, okay, of x n. All right, so I kind of wrote it using kind of mathematical kind of notation here, but just add up all the entries and divide by the number of entries. Okay. Okay, good. So that's the mean. The median is the what we call kind of the middlemost value. So to compute the median, you have to order all the data entries from least to greatest or greatest to least. And then you just pick out whichever one is the middlemost one. Okay. So you're going to do the same thing as we did with the quartiles. And so you need to order your data entries in ascending order, descending order, least to greatest, greatest to least, right? And then the median is just whichever one is right in the middle of the data set. Okay. Okay. Good. And then the last definition that we'll go over is the mode. Okay. Somehow switching the camera between the two USB ports fixes it temporarily. So okay. So the mode of a data set is simply just the entry in the data set that occurs most commonly. Okay. All right, and so the easiest way to to see the mode is to once again kind of order your data from least to greatest or greatest to least, and just find out which one kind of shows up the most. Okay. So, probably you guys have seen mean, median, and mode, probably dozens of times in your education, up until this point. Okay. Now, the reason these are a thing, and the reason that these are taught so much, is that the idea behind computing the mean, computing the median, computing the mode, right? This is not just busy work that they make you do in eighth grade, right? The idea behind these these quantities is to basically give you a way to represent what a typical or an average member of your data set would look like. Okay. Now, of course, the way that they compute the typical member is different, right? And oftentimes you're going to get different values for the mean, median, mode, right? But that's also the point too, because when you have a very complicated data set, right? Oftentimes the mean or the average value is usually not enough to kind of describe the whole data set, right? Which is kind of a problem greater than kind of just engineering in general, is that people kind of abuse, what I said, people abuse averages too much. And so people will look at the average of a very complex problem and use that to make kind of very oversimplified solutions or very oversimplified statements. And that's usually kind of ignoring a lot of the nuance and a lot of complexity in the problem, right? So oftentimes, it's good to actually have different representations for what a typical member looks like. So it's good to not only consider the mean, but also the median, and often the mode as well, because all three of those will kind of tell you something a little bit different about the data set. Because oftentimes, when you're collecting a lot of data, either just as an engineer or just even just in general, right? Oftentimes, what we say is that your data set is going to want to try to tell you a certain story, right? And so you can't really just oversimplify the story with just kind of one kind of simple one metric, right? Oftentimes you want to look at several metrics so that you best understand the trends, you best understand what this data kind of represents. Okay. Let me give you an example. And this data is a little bit outdated because I first kind of wrote these notes back in 2019, but let's preface it with that. Okay. Okay, so in 2019, there was data that was collected on the mean household income for residents in California. Okay. I'm sure the updated numbers, every year you file your taxes. By the way, today's tax day, so hopefully you guys filed your taxes. We get information on this, but just these notes were written in 2019, and so I have the 2019 numbers. Okay, so from that data, what they found was that the mean household income in California was $91,149. The 91,140. Okay. And that's the mean. Okay. So let's say you're reading an article online and you kind of see this number and you're like, wow, people in California are pretty wealthy, right? So, 91,000, that's still pretty good by today's standards. But in 2019, that was pretty good, right? So you could stop there and say like, wow, on average, California residents are pretty well off, right? But of course, the mean doesn't tell you the whole story, right? The mean is just one number. So if we took the same data set and say, let's compute the median household income instead. Median household income at the time was 63,787. Which is pretty different. And so that's about, maybe like a 35% drop, compared to the mean household income, maybe 30%. Okay. Right. Oftentimes, when you're thinking of a data, or when you when you first learn about the concepts of mean and median, oftentimes people kind of get these two confused, right? Because oftentimes they are the same. And so if you have a relatively balanced data set, which has kind of a Gaussian or bell curve distribution, the mean and median are probably going to be very close, if not exactly the same. Okay. But not every data set is going to look like that. Okay. So what could be the cause, or what's the difference, or what's the reason why these two quantities are quite different? Right, and so the answer to that, lies in kind of how we compute these, these different metrics. Okay. Okay, so let's talk about the mean first. So the mean is computed by summing up all of the, all the entries in the data set, and then just simply dividing by the number of people in that data set. Okay. Okay. Right, so that means when you compute the mean, because you're summing up all the data entries, right? If you have a big difference or a big variance between certain values of the entries in your data set, that's going to skew your data, right? And so the mean, oftentimes what people say is that the mean is often skewed by outliers in your data set. And that could be outliers in both directions. And so, for California household income, these are outliers on kind of the higher end, right? And so if you think about kind of, California is very diverse, but one thing that attracts people to California is the weather. So you have a lot of celebrities, athletes that are living in California that have very large incomes. We have a lot of tech bros that kind of live up in NorCal that have Silicon Valley salaries, and that's going to skew the data as well, right? And so when you have these outliers that are kind of very outsized or have much larger values or much different values than most of the other population in your data set, that's going to skew your mean. Okay. Whereas the median, right? Oftentimes, people say the median is a much better representation of kind of the typical experience, or the typical kind of entry for a data set like this. Okay, the median represents literally the middlemost entry within that data set. Right, so you order the data, you order everyone in the data set from least to greatest or greatest to least, the median is right in the middle of that. Okay. And so the benefit for the median is that, the median is not, the value of the median is not skewed by any outliers, because, an outlier may be, maybe a huge outlier. So maybe, we have, maybe 3 people in California with an income of, maybe $300 million, right? That's way, way different than, let's say that, even the 100th entry. But the median doesn't care. The median just says that, all right, you're number 1, and then the next person, number 2, number 3, number 4. So, there's no additional weighting, if you are kind of way, way different from the groups. Okay. So which one's better, right? So, oftentimes people say that the median is better for representing these things. The answer is neither, right? So the answer is, not one is better than the other one, because both tell a different side of your data set, right? The correct answer is that, you really need both. And honestly, you probably even need more metrics to kind of really understand this data set, because, when you have such a complex thing as, all the household incomes in California with the huge population that we have, right? You can't really distill it or sum it or kind of, simplify it with just kind of a couple different metrics. Okay. But you can see that even just reporting 2 or getting knowledge of these 2 metrics tells, a very interesting story about this data set. Okay, any questions on mean, median, mode? Okay. So, I think this is particularly relevant nowadays too, because, a lot of times you'll kind of read things online, and, a lot of people can have an agenda, I guess you could say, right? And so they'll use certain statistics or certain numbers to kind of make their argument. And, you kind of have to be a little bit critical of, what does this number actually represent? And it's not that people are lying, right? So these numbers, those numbers probably they do exist. They didn't just make them up, but there's lots of different ways that you can take the same data set and kind of spin it in a way, depending on how you measure the metrics, how you analyze it, how you measure the means, things like that, to get a certain point across. So, always ask, let me, give me some more information about this data set, because oftentimes just one number is not really enough to understand kind of a full data set. Okay. All right. So I think the last thing we'll have time to talk about today is this idea of variance and standard deviation. Okay. So variance and standard deviation, these are additional metrics that you can use to measure a data set, right? Or to kind of, tell some information on the analytics or the statistics of a data set. Okay. But it represents a different side of your data, or a different aspect of your data set compared to the mean, median, and mode. Okay. So like I said, the mean, median, and mode, they're all kind of similar in the sense that they aim to kind of represent what a typical member of your data set looks like. In contrast, the variance and the standard deviation, these tell you, how varied your data set is. So how much your data is going to vary from entry to entry. Okay. And oftentimes, this is something that's very important or something that is, very interesting about your data set because you want to see how varied your things, your entries are, right? Because like I said, oftentimes, a lot of the intricacies and a lot of the nuance in the data set or random variable is kind of masked by the mean or the median, okay? So let's just do a very, very quick example. Okay. So let's consider two data sets. And so we'll say we have data set A has these values. We have data set A consists of -2, -1, 0, 1, and 2. Okay. So we have a 5-entry data set there. And so, you can kind of just see very quickly here that the mean value and the median value are the same in this case. And so both of those are 0. Okay. Okay. And then let's look at data set B, right? So B is a separate data set, and it's gonna be a data set with the same mean and median, which you might argue, these two are the same data set, they have the same mean, but it's gonna be very clear that these data sets are gonna be very different from each other. So data set B, let's say, is going to be consisted of -200, -100, 0, 100, and 200. Okay. So once again, even with data set B here, we have a mean and a median of 0. There's no mode because every entry is unique. All right, so two data sets with the exact same mean and exact same median, but I think everyone agrees here that these two data sets are very, very different from each other. Okay. So how can we kind of quantify these differences? Well, we know that in data set A, right? Data set A, the entries are all very close to each other. So the entries are only separated by a value of 1, right? Whereas an entry in data set B, the entries in your data set are much more varied. And so entry to entry, the variance is up to, well, they are 100, right? And so, the idea with the variance and standard deviation is to quantify these differences so that we can actually say that these two data sets are indeed very, very different from each other. Okay. So the way to compute the variance is we have a formula for it. Okay, so the variance is given by the following formula. So oftentimes, we express the variance as the symbol sigma. Okay. So sigma here represents variance. And it's equal to 1 divided by big N minus 1. So big N here once again represents the number of entries in the data set. So however many times you measured or you took a measurement. Okay. All right, we have summation here. Summation from little n is equal to 1 to big N. Okay. And the quantity that we're summing is the following. So xn minus x line, so that's the mean quantity squared. Where x with the line over the top, this is the same as before. So this is the mean of the data set. Okay. And so what we're doing is we're taking each individual entry of the data set, we're subtracting it from the mean, okay, and we're squaring it, and we're summing up all of those entries. Okay. All right. So to kind of put this equation in words, take difference between each entry of the data set and the mean. Okay. Right, so we're taking each entry of the data set, subtracting it from the mean, okay? We square it, and the reason we square it is to just make sure that, we all get positive numbers. So that's kind of the most popular way to get a positive number in mathematics. And so I know, the question I've asked this question since I was a freshman in college. Why don't we just take the absolute value? Absolute value gives us the same thing. Absolute value is too fancy. So kind of the typical thing is to square things when you want a positive number. Okay. So for each entry in the data set, we're going to subtract the mean, square it so that we get a positive number. Okay. Sum all of those up. Okay. And then we're going to divide that entire quantity by n minus 1. Okay, so the reason we do n minus 1 and not n is just to account for the fact where if we have kind of a one entry data set, it doesn't make sense to have variance in a one entry data set. And so if your big N is 1, then you would get an undefined variance. And so variance is only defined for a data set of at least 2. Okay. So that's why we have n minus 1, just to make sure that variance is kind of entry to entry. So if you have a data set of 2, that means your variance is just between those 2 entries. Okay, so that is the variance. Okay. Variance actually has units of quantity squared, and so oftentimes you'll see what's reported is the standard deviation. Standard deviation is nothing more than just the square root of the variance. So standard deviation, which is sigma, is just square root of sigma squared. Standard deviation is a bit more popular just because it has the same units as the mean, but both kind of represent kind of the same thing. Okay, so with the variance and the standard deviation, you'll get a sense of how much your data entries are varying from one. Okay, so it's just something else that you can compute in addition to the mean that tells you information about your data set. All right, any questions on this before we wrap it up for today? Okay, all right, so that's it for today. So when we come back on Thursday, we'll start talking about talk about random variables and probability distributions, and so we'll get more into that. And then next Tuesday will be the midterm. So thank you guys for coming today. Hope you guys have a good rest of your day. I will see you all on Thursday.
Because I have one this week, World 1, then I have 2 next week. I took all my this week and then we were gonna a midterm for design class,
That's
but then he was like, I feel bad for it. That's so nice.
Well, here, that we usually do. Yeah, literally standard deviation variance. We have like 2 slides right there. Like that.
You guys are presenting on this?
Yeah.
Probabilities.
Oh, nice, perfect. This is coming out at a good time then.
Yeah. Thanks.
See you guys.
Have a good one.